And for Unit 5 now, we are on to minerals. And as promised earlier, there's going to be a fair bit more chemistry in this section. And I am sure that I will gloss over some stuff, so please, please, please let me know what I need to come back and make some auxiliary PowerPoints for, or if you want to get in, collaborate to learn about certain things, I can do that with you. Let me know where I can help, and I want to get everybody on the right page with this chemistry that's about to come. So I wanted to review a bit of the chemistry, depending on what you've had so far and where you might be on these particular things. You may need some more support. Just let me know. We can do that. I know this can be fairly simplistic, but just to make sure that we get there, I want to talk about element symbols. Somebody brought that up in today's lab. And then I want to talk about chemical formulas. And, I intend to go a little deeper on this when we get into especially the silicates. So there will be more to come on this. I'm going to start with what for mineralogy is a relatively simple one, but for chemistry class, it would not be a simple one. Then I want to talk about periodicity and ions and radii. So I haven't really put together specific slides on this, and I don't know where folks are going to be. Do you remember ionic versus covalent bonding from high school chemistries or whatever? The covalent version is where you have sharing of electrons between adjacent atoms. This would be an example of like the bonds in diamond, where the oxygens, where the carbons are linked up one to the next. And so if I ask in a carbon-carbon skeleton like this, which carbon of these C's, which carbon would be strong enough to pull away an electron from the other carbon? And the answer is neither. Neither is stronger than the other in electronegativity is the value that we're talking about. So this carbon can't steal this carbon's electrons, and this carbon can't steal this carbon's electrons. So they end up sharing them back and forth. And that is as opposed to ionic bonding, in which you have something like let's change colors here. You have a sodium, and it's got its electrons out here, and importantly, it has one valence electron on the outside. And then you have this chlorine, and it's got 7 electrons out here in its valence. And if you think back to prior chemistries that you might have heard of, 8's kind of a magic number. It's a little bit of a simplification, but it'll work for now. So this chlorine really, really wants 8. And this sodium has 1 kind of hanging out here that it doesn't really know what to do with. Well, what happens is this chlorine just straight up steals that electron from the sodium. Now, in the process, this sodium has lost a negative charge in the form of that electron, so it's now a positively charged ion, and this chlorine has gained a negative charge and is now a negatively charged ion. Then what happens is, because you have a positive attracted to a negative, these guys essentially are in an electrostatic bond with each other because of those opposite charges, and that is an ionic bond. All right, and then lattice systems are where you have these arrangements of atoms in a bond system, and you have a crystal lattice, and that's just the 3-dimensional network of how the atoms arrange together. Some details about the chemical symbol. We talked about this a little bit in lab today too. So from a periodic table, you get this 1 or 2 letter code that tells you what the element is. In this case, Pb is lead, so Pb will always mean lead. It's made from the Latin name for the mineral. So some of them, like Cl for chlorine, makes sense. Br for bromine makes sense. O for oxygen, but Pb for lead because of the Latin name, which is plumbinum or something like that. I don't really know Latin, so I'm just guessing at how it's pronounced. Okay, so that's the code there, right? But then elements are actually determined by their atomic number. And that is exactly the number of protons. So lead has 82 protons in an atom of lead. Every atom of lead has exactly 82 protons. And every atom containing 82 protons is lead. So that is locked in, no way out of it. 82 protons is lead. Okay, that's how it's determined. The other number, however, the mass number, that one floats a bit. This one does fluctuate. So the way it's calculated, and please don't divide it in half. I don't know where that came from. I see it every time I teach either a chemistry or a geology course, and it doesn't work. So it is, the mass number is the total, the sum added together of the protons plus the neutrons. Well, because it's lead, we're guaranteed that there have to be 82 protons. For lead 208, then, that only leaves 126 neutrons. And just let me reiterate, look, that's not divided in half. There are not 104 of anything here, okay? So it's added together to get the mass number. All right. So now let's talk about this number over here, which is the charge on it, the ionic charge. Okay, so a neutral atom of lead, well, we know it has 82 protons because it's lead. Well, a neutral atom would have to have 82 electrons orbiting around it also in order to balance out the charge. 82 protons with positive charges each, then 82 electrons with negative charges each, and they balance out. But in this case, this tells us, well, we must have lost 2 of the negative charges, and we have an imbalance. So we have 82 protons, 82 times positive 1, and we now only have 80 electrons, 80 times negative 1. So 82 protons minus 80 electrons gives you a net charge of positive 2. Okay, so that's a net charge on the ion. Okay, chemical formulas. And we'll start with, like I said, for geology, a relatively simple one. This is the chemical formula for dolomite, one of the minerals that, well, actually, it's not in your set to identify, but we can talk about how it would be very similar to calcite, which is in your set. Okay, so a little detail here. The capital letters tell you that we're starting a new element each time. And remember that capital C, capital O is a different thing than capital C, lowercase o. So capital C is carbon. Capital O is oxygen. It's not cobalt, which would be a C, little o. So we have inside, I'm working inside the parentheses first. This is called a carbonate unit, or a carbonate anion. So we have a carbon, and then oxygen followed by the subscript of 3. So we have a carbon and 3 oxygens. That is a unit right there. Okay. Parentheses. This 2 tells me that I have 2 of those carbonate units. So that means all total, if I could just break it down and count individual atoms, I'd have 2 carbons, and I would have a total of 6 oxygens, 2 times the 3. Okay, so that tells me I've got 2 carbonate units with a couple of carbon atoms and a total of 6 oxygen atoms in them. All right, this magnesium right here, Mg is magnesium, and there's no subscript, so that means there's 1 of those. And this calcium, again, no subscript, so there's 1 of those. Okay, remember that the Periodic table is like the best cheat sheet ever invented. There's so much information on this thing. So these are arranged in columns, okay? Periods, groups, periods go across, groups go up and down. All right, so everything in the noble gas column, remember that magic number 8 that we were talking about? Well, it's over here and it's full. So these guys don't play. They do not tend to ionize. Now that's a simplification. When you get down here to these big guys, it does change. But for our purposes for this course, you can say that the noble gases are unlikely to bond with anything. Okay? But this column, the halogens are one short of it, and they are likely, like chlorine did earlier, to steal someone's electron and end up with a -1 charge. Very similarly, this group is likely to steal 2 electrons, like oxygen does, and end up with a net -2 charge. Okay, I'm going to skip to the other side of the table for a reason. Let's go all the way over here. So these, look at lithium, it's 3. So a neutral atom of lithium comes with 3 electrons, and it really doesn't care about that third when it's just kind of hanging out there by itself. It's easy for it to get stolen. So when it loses an electron, it ends up with that net +1 charge because it's a net. Similarly, these guys will have 2 electrons that are easy to lose, and they will easily go to a +2 charge. Okay. Those 5 columns, you really should memorize those. Those 5 columns are going to be so important to any chemistry you do. These others that I skipped over here on the right, I did that because they're a little less solid on how they act. The nitrogen containing group, it is fairly likely to go to a -3. But I'm going to try to write this smaller. It's a little bit likely to go the other direction and lose 5. So you can see it could gain 3 electrons, 1, 2, 3. Or it could lose 1, 2, 3, 1, 2, 3, 4, and the 5th one, and lose all the way back to the helium configuration and be +5. Okay, so that one's a little confusing. And carbon is really stuck right in the middle and tends to be covalent. Nitrogen does a lot of covalent also. Carbon likes to do covalent. And then these guys tend to be +3s, but again, you're not as cleanly locked into +3s on that. So just know the periodicity of it, and you can count them directly off the table. I would also note that, let me do a highlighter here, let's do a yellow highlighter. Everything in here, get the charge from me, because it changes. We have, look at iron right here, where I'm circling in the middle. We can have iron 3+, we can have iron 2+, we can have chromium 3+. This lists the chromium 2+, but probably more common than 2+ is 6+. There are a lot of things that you can have. Titanium 4 and 3. You can have lots of stuff going on in here. Okay, so these are called the transitions. All right, ionic radii. We're not going to get super deep in, but it's going to become a little bit important when we talk about different cations substituting in especially the silicates. But this example is not a silicate. This is just a sodium chloride. Very simple lattice. That lattice that I was talking about a few slides back. It's just this arrangement in 3 dimensions of everybody in a nice stacked array here. And if you can see, that's a little sodium cation. This is a bigger chloride. It's a chlorine anion. We tend to put an IDE on the end of it and call it a chloride anion. You can see here, This is atomic force microscopy. Is not the actual export from the analytical technique, but it's kind of a contoured version of it. We contour all kinds of things, not just elevations like we did in that lab number 2. So you can see where this little tight circle where the sodium cation is versus this bigger chlorine. And so you can measure across them, and they have a radius here. Chlorine is much bigger than the sodium. That radius matters as to what will fit in this lattice if you go to substituting other things in here besides the sodium. If you try to stick a potassium in here, it's not going to fit very well because it would be big compared to this sodium. So what's the point of the chemistry? And that is to talk about minerals. What are minerals? So that USGS definition that we talked about earlier. So a mineral is in each of these parts we're going to take apart here. A naturally occurring. Okay, so we're going to take that apart. Inorganic. So that's going to be another piece of it. Element or compound having an orderly internal structure. That's the lattice that I was talking about a while ago. So we'll talk about those. And then a characteristic chemical composition. That's your formula. It has to have a certain formula. Okay. We need a crystal form from the formula. Won't always be in a crystal, but it has a crystal form nonetheless. And finally, it has unique physical properties, which is what we've been talking about in lab. The hardness, the density, the cleavage planes, all those different things are the physical properties. So we're going to take apart each part of that and talk about what that means within the different mineral classes. So minerals have to be naturally occurring. So this rules out constructed crystals. You can make a whole lot more crystals than nature has made. Although I am seeing an argument being made in some of the literature right now that if we can make it, nature probably already has made it. And so some folks will argue this, but if we construct a crystal that doesn't exist in nature, then that's not naturally occurring. So it would not fit the official definition, at least. And there's another piece to this. So we only have, we think, naturally occurring elements up through number 92 uranium. So something like plutonium, which is 94, we think that plutonium probably is not naturally occurring at all, that it has never just naturally occurred in the universe, and all plutonium that has ever existed has been made in a nuclear reactor. Well, so if that's the case, then plutonium itself is not a natural element, and so a plutonium oxide crystal would not be considered a mineral by this definition. It would look like a mineral and act like a mineral, but we would let it be called a mineral, I guess. And then second piece, the inorganic. In chemistry, we tend to divide chemistry overall into a couple of classes, and that is organic and kind of everything else, inorganic. So organic chemistry, it's a little tricky to define what it is. It's mostly based around covalent bonds from carbon, usually to other carbons, but also including to nitrogen, oxygen, hydrogen, and then other atoms. So they'll stick in other things, especially halogens and stuff. But really, it's about the carbon bonds. Okay. So what they're really going for is life produced. Okay. So if you have a protein crystal, so I did some work at UAB where we were actually crystallizing proteins that we actually changed the DNA in a E. coli bacteria to produce human proteins, and we tried to crystallize those. So even though we could crystallize them, we could X-ray them and get a good crystal form and stuff, they're life produced. So they're not inorganic. Okay, so those don't count. Anything that got produced in your body, kidney stones are a good example. They're mostly calcium carbonate, and they don't count as a mineral officially because they are life produced. Minerals are required to have an ordered internal structure. This is the lattice that I was talking about earlier. And so this is a simple lattice displayed here. So whatever this mineral is, this could be sodium chloride like before. Whatever this is, every version of this mineral has the same structure. And that's what gives it all the properties and everything else that we're going to talk about. But to be a mineral in the first place, it's got to have one of these. It's got to have an internal structural arrangement of its atoms in an orderly fashion like this in a lattice. So if it doesn't have a lattice, it can't be considered a mineral. And that is interesting that it rules out a couple of things that you might think of as. If you've ever seen the gemstone opal, I mean, it looks like a mineral, but it isn't. Because it doesn't have this orderly internal structure. It's kind of a random assortment of globs of silica stuck together. Obsidian is another example. Obsidian is a naturally formed glass, but a glass is defined as absent this structure. So it's solid, but it doesn't have this internal array of atoms like this. So it doesn't count as having a lattice, and it doesn't count as a mineral. Okay, characteristic chemical composition. Now, on the simple version, this just means it has a chemical formula that we can be sure of. Unfortunately, the simple is not necessarily going to hold because we allow for some variation in this formula, and we'll talk about those under the specific mineral classes, where you can have some different composition. But basically, think of this set composition as what the chemical formula is. So that dolomite that I did earlier, let me put it back up there, with Ca, Mg, CO3, sub 2. Well, that's dolomite. Well, I can be sure that dolomite's going to have 2 carbonate units per unit cell. It's never going to have 3. This is set. This is set in stone right there. Okay, all minerals do have a crystal form. However, and this is important, all minerals do not show crystals that you can see with your eye. Those are called, we have a word for it, euhedral. Okay, euhedral crystals are ones that you can see with your eye. So, subhedral crystals are some that maybe if you use a magnifying glass or a microscope you can see them. We call them subhedral or microcrystalline. And then there's even a level below that called cryptocrystalline that you cannot see even with a microscope. And the way we see that crystal form is we use an X-ray analysis. We'll actually X-ray the minerals, and what happens is the X-rays are short enough wavelength that they will refract off of the actual atomic layers inside the mineral, and we get a refraction form that is diagnostic of the specific crystal lattice inside a mineral. And this is the gold standard for how you identify minerals is you X-ray them, because that X-ray form is rock solid on what kind of mineral you have. And then I'm going to spend the rest of this slideshow talking about the physical properties of minerals. You've seen some of these in the lab already. This is really in practice what we do most of the time if we can't get to an x-ray of how we determine what minerals are. So color, sort of. You can't trust, and I'm going to get to a slide on that. Well, I'll save that to talk about it. Hardness and density, luster, cleavage. We've talked a lot about cleavage in lab because it's so hard to try to figure out what the particular cleavage is sometimes. Sometimes it's easier to see that it exists. Crystal form, remember that doesn't necessarily have to make visible crystals. Magnetic susceptibility, I think I put luster on here twice for some reason. So reactivity, we'll talk about a little bit in the form of acid, but you could talk about other kinds of reactivities. And then taste. So be very careful of using color to identify minerals. Here's an example of why. So these guys are all beryl. This is the mineral called beryl, B-E-R-Y-L. Here it is right here. So you have this light blue version, you have this pink version, and you have this green version. Well, these are seriously small amounts of. In the case of the green here, it's a little bit of chromium. In the case of the pink, has a little bit of manganese. And in the case of the blue, has a little bit of iron. But it does not take very much. I mean, we're talking about literally 1 atom of iron for at least 10 to the third, maybe 10 to the sixth crystal units in there. So just almost undetectable amounts of these cation impurities in there, and you get this color. Sometimes it's a nice deep color. That is actually called emerald. So instead of trusting bulk color like that, we tend to use a powder color, which we get by streaking it across that streak plate that we used in lab. And you get a powder that is more the color of the mineral without the impurities. So hardness, we tend to use relative hardness, Mohs hardness scale, which is just 1 to 10, and it just sets up various minerals as pegged at 1, 2, 3, 4, all the way to 10. Right? Diamond being 10 and the hardest. Corundum is pretty close. And then you get other things that you can start to get in between. This puts steel at 6.5, and that's a pretty good stainless to be at 6.5, and you're not likely to. You can get a hard, like if you use grade 8 bolts or something like that, they might be 6.5. A file is likely to be 6.5, but most of your glass is like a knife. It's going to be in between 5 and 6. And in Labo's telling you that a really good knife, like a Swiss, is likely to be 5.5, whereas most blades are going to be 5.2, 5.3. Copper is another good diagnostic, and your fingernail is a good diagnostic as well. Also, a big trick that I learned to use is to test minerals against each other. So you've got a knife at 5.3-ish, right? A piece of glass at 5.5. But then you've got this feldspar that, well, it's sitting right there above it, and so it scratches the glass. You go, okay, it's greater than 5.5, but how much greater? Hey, I happen to have a quartz crystal lying around, so I can test the quartz crystal against the feldspar to see which of those is harder. Also remember that this is a two-sided test. You can try it both directions. You try to scratch the feldspar with the quartz, but then go the other direction and try to scratch the quartz with the feldspar. One of them is going to win and scratch the other one. The harder one scratches the softer one. Luster is a surface effect from minerals, and it has to do with what the light waves are doing as they get into a surface effect. And so you get This is really hard to just explain with words, but you get this blending effect like you would see with a metal surface, or a vitreous effect like you would get with a glass. Then earthy is kind of easy to see because it's almost like it's not luster. You can see silky where they look like they're fibrous, pearly, greasy. There's a bunch of other kind of lusters. And so you just kind of have to train your eye to see those, look at a bunch of different ones, and decide, well, okay, that's what they mean when they're saying metallic luster. All right, let's talk about density. So the top row up here is hopefully giving you kind of an intuitive idea of density. We could look at the density of 1 cubic centimeter of air. The mass would be 0.001 grams. Air doesn't weigh very much, right? An exact same amount of water would be 1.00 grams. So you see how much heavier an equal amount of water would be. You can do the same thing with lead. Lead would be a lot heavier than water, and then uranium heavier still. That 1 cubic centimeter of uranium would be 19.1 grams. Okay? So same thing happens with minerals, and we can look at their relative densities. So quartz is one of the light minerals. It's only 2.6 times as heavy as water. Okay? I mean, it's going to sink, obviously, but it's not that much heavier, that much denser than water. Kyanite's a little more. You can see that one at 3.6. Garnets are noticeably dense. When you pick them up, you're like, wow, that feels denser than most rocks. And then something like a barite, very dense at 4.5. Then something like we saw a galena, lead sulfide, in lab, and it's 7 point, I want to say 7.6, 7 point something grams per cubic centimeter. But that's density. Mineral reactivity is usually just talked about in terms of whether or not it reacts with an acid solution. So what I've been using in lab in some of the videos is a dilute hydrochloric acid solution, usually 0.1 to 1 molar. The one I'm using is 1 molar so that it gives a clear look on the videos. I want you to be able to see the bubbles, the effervescence in it. There are some special cases where it gets a little trickier. So like calcite reacts with cold HCl, but dolomite you have to powder it or heat it up to get it to react. And then if you've had chemistry lab where we looked at whether or not a reaction occurs, that's what we're looking for here. Okay, cleavage. Cleavage we spend a lot of time on in lab, and so here in lecture I want to talk about the theory behind it more than the actual what's going on. Think back to those lattices we talked about earlier. So this idea of cleavage has to do with there being weak planes in a mineral lattice. Okay, so because this is based around the way the atoms line up in that lattice, it repeats every crystal unit. So if biotite and muscovite have all these covalent bonds linking their sheets together, but in between those sheets they just have a very weak electrostatic force. So you see that along the sheet itself it's much stronger than it is in between. That's why biotite and muscovite show that strong cleavage, one direction of cleavage, because it's in between their sheets. This is typical of a whole class of minerals called phyllosilicates that we're going to talk about later. But it's because let's call it X, Y, and Z, if you think about 3 dimensions, right? In the X direction, in the Y direction, these guys are all linked together covalently. But in the Z, the up and down direction, they only have weak bonds in between their layers, and so you can peel those layers apart. That's one direction cleavage. Now you can extend the same idea to things that have 2 good directions of cleavage, or even more. with 3 directions of cleavage in the case of galena, or halite. Halite, we looked at the structure early on with the sodiums and the chlorines, and they line up in those cubes, and lo and behold, halite tends to cleave into cubes the same way. One other thing I want to mention is in the case of something like quartz. So quartz is we'll get to this later, but it's a tectosilicate, meaning that all it has is SiO2s, and they are in this complex three-dimensional web stuck together. Well, because of that complex three-dimensional web, there is no certain plane of weakness. So it's strong in all the directions. So if you get quartz to break by applying a hammer or something like that, it doesn't break in planes, it just breaks like untempered glass in these shards and curved surfaces that we call conchoidal fracture instead of having a good cleavage. Here's our one direction of cleavage with the micas, phyllosilicates. You can see it kind of stacked up here. Or you could have 2 directions of cleavage, and this is an example of 2 directions. And if you see the planes here, you can see how they've got this diagram set up as 90 degrees. So these 2 planes of weakness intersect each other at 90 degrees, and you can see it here on the mineral how that edge is a nice 90 degrees right there. So 2 directions at 90. Or you can still have 2 directions, but they don't line up at 90. See how they've got this plane, this yellow plane, they've got it tilted from the vertical. It intersects at something other than 90. And this is a beautiful crystal of titanite that has, you can see that angled intersection there. Or you could say, well, now that last one had the 2 good directions, but the end of it was just kind of choppy. And that's true. It just breaks on the end. It doesn't have that 3rd plane. Halite, on the other hand, has, this is the top surface, that's a plane. Then you got this side over here on the left, that's a plane. And then this side in the front, that's another plane. And those 3 planes intersect each other. You can see it here in the diagram at 90 degrees. And that's an important characteristic of halite. It's called cubic cleavage. And if you look carefully in this sample, you can almost see how right here, another cube is ready to break out. Remember that repeats all the way through the crystal structure, every set of atoms, every crystal cell. And so you get cleavage planes all the way through the crystal based on those planes of weakness along the gaps between atoms. And of course, those 3 cleavages could be at something other than 90. And this, you can see the tilted planes here. So if they do that, you get something like rhombohedral cleavage, which is 3 directions not at 90. Those other, I put the sources for where I got the other images here, but this one I wanted to point out because if you follow this link from the PowerPoint, it'll take you to a whole lot of cleavage structures, and you can take a look at them and get familiar with what they look like. I like this particular link very well. A little more complex when we get to 4 directions of cleavage, and there's a video up that shows the 4 directions of cleavage quite well. It's in the extra stuff in the background materials. So these 4 planes, you have to look at them as, so plane number 3 here, look at it as flat along the top of this. And then 2 is leaned in towards 3, 1 is leaned in towards 3, and 4 coming back towards me would also be leaned in towards 3. So none of those are parallel, 1, 2, or 4. And they also intersect 3. So they are 4 independent directions. This is typical of fluorite is one example of it, and we call it octahedral cleavage. You can see that this would be a hedron with 8 different sides. And if you have context for any dice-based games, you might have seen an 8-sider before. That's an octahedron. And none of the samples that we deal with, this is wrong, and I'm going to mark it out right now. That's not fluorite. It is called sphalerite. I'm going to try to write it with this pen here. Yeah, that's a nice E, huh? Sphalerite. Sphalerite has lots of directions of cleavage. I believe it's 6. Let's see. It should be 6. Apparently I didn't change that. I should have. So I did change this, though. You can see a whole bunch of different planes of cleavage in that. Okay? And we don't have one of these to worry about in your samples, but just know that it can get more complex than what you have here. Crystal form you have to be really careful with. We're not trying to identify museum specimens usually, and so you're probably not going to see that many really beautiful crystals. The ones that you might see, cubic crystals like in halite, or you can see a lot of quartz crystals. They're fairly easy to come by. But for the most part, you get cleavage fragments and chunks of minerals instead of nice, clean crystals. There is a really pretty gallery here that I put a link to in case you want to go look at these crystals that we're talking about. And these are all different crystal forms. And these are all out of the Johnson text in section 3.6. But you can start to see, well, these are cleavage fragments really, but you can have octahedral crystals. Diamond tends to make octahedral crystals. But you can also have other kinds of euhedral crystals, big things that we can see. You can have other forms. You can have these cavity fills. You can have dendritic. This is actually crystallization on a surface. It's manganese oxide. You can have big tabular ones. A lot of different examples covered in the Johnson text. And in the next video, we'll dive into the non-silicate mineral types. We're going to talk about each of those in the next video, and then we're going to talk about silicates on their own, because silicates are so incredibly important. Remember that our lithosphere tends to concentrate silicate or silicate-loving elements in the lithosphere, so that this is a lot of what the part of the Earth that we interact with is made of. See you in the next video.